Finally, let's wrap everything up related to Fourier-Bessel series, and let's combine the results of the two previous videos where we said that if we have a function f of x, that we can write that as a sum of Bessel functions, namely Bessel functions of a certain order n, and of with scaling factors psi I of x, where these psi i's, they were actually the zeros of that particular Bessel function. So the summation index runs from 0 to infinity, and then we have the expansion coefficient a sub I. And then by making use of orthogonality relationships, we were able to calculate that a sub I is the integral from 0 to 1 of the scalar products of our function f of x with this particular basis function. Okay, f of x dx divided by the integral from 0 to 1 of x jn squared psi I x dx. Or if you really want to again make use of the notation with scalar products, this is the scalar product of basis functions jn psi I of x with f, and then jn psi I of x, and I'm running out of space here with itself. So this is the normalization integral. Now in another video, we've calculated that this thing is equal to jn plus 1 squared psi I divided by 2. So finally, we have our explicit formula for the expansion coefficient. It's 2 divided by jn plus 1 squared psi I times the integral from 0 to 1 x jn psi I of x f x dx. Okay, so this was just combining the results from the previous videos. But let's now wax philosophically about this formula here, because you might say, well, we can calculate this if you know f, then you just calculate this thing numerically. But why on earth would you expand a known function in this series expansion here, apart from mathematical bragging rights? So what's the use of expanding a known function in Bessel functions? Well, the thing is, in practice, we're often not working with a situation where f is known. So often f is unknown, but we do know a differential equation for f. And then the situation becomes different, because then we can start from a certain ansatz where we say, okay, I'm looking for an unknown function f, but the differential equation has some relationship with cylindrical coordinates, so perhaps it makes sense to approximate this function with a finite set of basis functions, so up to a finite number of our Fourier-Bessel series here. So that way, because these basis functions incorporate some of the physics of the problem, you might hope that you need few terms in order to get decent numerical convergence. Then you have an unknown function f expressed this way, and then you can take this particular form, substitute that into the differential equation, and then do lots of fun mathematics. But hopefully at the end of the day, you will be able to derive a certain linear system that will give you your coefficients a sub I. And that way, that's a technique that people often use when they want to calculate solutions to differential equations, starting from a certain series expansion with a finite number of terms. And if you've chosen your basis functions cleverly, then hopefully you don't need that many terms in order to get a good result.